Alright, now we're going to get to the actual use of similarity. Last section we talked about ratios and proportions because they're going to be handy for explaining these kinds of things. Without understanding ratios and proportions, this section becomes much more difficult. So if you don't understand ratios and proportions, go back, rewatch the last video, come talk to me during tutoring, whatever you need. That way we can make sure that you're going to be able to fully understand this. I would take this idea of similarity and apply it to polygons. Again, any figure that's closed, all exterior points, all that stuff. Squares, quadrilaterals, pentagons, triangles. We're going to examine all of them in general right now before we move on to specific ones like triangles in the next section. The objectives for this section: identify and apply the conditions of similar polygons, and then identify and explain the golden ratio. So be able to look at the rules and be able to apply the rules, and a very specific one, the golden ratio, which has a lot of historical and architectural and artistic implications. The polygons, so here's a quick definition. Two polygons are similar, and here's the symbol for similar. It's like the congruent sign, but it lacks the equal part. So two polygons are similar if corresponding angles are congruent, so that's not changing, and corresponding sides are proportional. This is the difference between congruence and similarity. For a polygon to be similar, the angles that are corresponding are congruent and the corresponding sides are proportional. When we talked about congruence, yes, this was true, but here the sides are also congruent. So now we can have things that look the same but are different sizes. So similarity has similar properties but a different size, whereas congruence is specifically the exact same. So there's a little bit of difference here. When I say proportional sides, what I mean is that the ratio of two side lengths of one figure is equal to the ratio of the two corresponding side lengths from the second figure. That's what proportional means. It means I can take the ratio of two sides, compare it to the ratio of the corresponding two sides for the second figure, and they will be equal, and that makes it a proportion. So that's why it's called proportional. Here's an example. Let's say that I had these two isosceles triangles whose vertex angle and base angles were congruent. So that meets, so it's not showing up very well, there we go. That meets the first criterion. Corresponding angles are congruent, which we've established. The second part, though, is that they must be proportional. So let's say this was 1, 3, 3, and this one was 4, 12, 12. And the question is, are these sides proportional? If they are, and with the angles being congruent, we have similar figures. In this case, similar triangles. So what we do is we take the ratio of any of the sides. 1 to 3 would be the angle of this base to one of the legs. So let's take the proportion of this base to one of these legs also. So for the bigger triangle, it would be 4 to 12. And the question is that expression true? Is this comparison of two ratios an equality? If it is, we call it a proportion, and these become proportional. Well, 1/3, and we reduce 4/12 to get 1/3, and we find that this is actually true. I could do it for the other sides just to make sure, but I compare any of the sides as a ratio to any of these sides, or the corresponding sides as the ratio, and I find that they produce two equal ratios, so it makes a proportion. And when it makes a proportion, we say the sides are proportional. Again, not congruent, because obviously this one's bigger than this one, but because the angles are congruent and the sides are proportional, we can say that this triangle is similar to this triangle. And to do that, we would just take the triangle and we would say like that. Those two triangles are similar. The same way we used congruence mark earlier, but now we're getting rid of the equality because they're not really equal, but they are similar. There's a very particular ratio that's good for us to know. And this thing called the golden ratio. Now the golden ratio shows up a lot in architecture. The ancient Greeks first, well actually they first done it, but the ancient Greeks understood it. They understood it as very appealing to the human eye for whatever reason. So a lot of the Greek architecture uses the golden ratio. There's a lot of natural things that use golden ratios. Nautilus shells, sunflower patterns, pineapple patterns, all use golden ratios. And the first application we're going to use the golden ratio is this thing called the golden rectangle. It's a good way to define it. So a golden rectangle is a rectangle that can be divided into a square and another rectangle that is similar to the original rectangle. So, here's my original rectangle. This is not drawn to scale, but it's pretty close. There's my original rectangle. I divide it into a square. So I find this length here and basically make it form this shape here. And the leftover, if this leftover is similar to the original black outlined rectangle, we call it a golden rectangle. Again, to be similar, the angles have to be congruent. Well, these are 4 right angles. 1, 2, 3, 4. And then by construction of being a square, those are 4 right angles. So the corresponding angles are congruent. That's the first criterion. And then we actually have to go through and check the ratio to see if it was similar or not. If this was proportional to this, if this ratio is proportional to this ratio, then it would be a similar polygon. And when we have that, we call this a golden rectangle. Then we could go from there, cut a square, and see if that one was golden ratioed. And actually what you can do is you can produce an infinite number of golden rectangles from one, just by cutting a square out of it and analyzing the remainder. You could also make this part of a bigger golden rectangle by finding how long it needs to be and just extending it upwards and making a larger one. The science and math behind it are actually very cool. We don't have enough time to go into it right now, but I hope that you go get into higher level math courses where you see different expressions of the golden ratio and golden rectangles and stuff like that, because it is very interesting. It's odd that it shows up in nature. It doesn't seem like it's a coincidence. There seems to be something kind of behind all of this. And you can explore the math and the science and the philosophy behind that if you get to a higher level math course. Take a golden rectangle and it produces the golden ratio, which again is the length and the width of a golden rectangle. So this length by this width. And you find that this is not an exact number. This is actually a number that is irrational, like pi or square root of 2. And you find that this ratio is about 1.618 to 1. It's not exactly, this actually goes on forever, this decimal, but it's close enough. 1.618 to 1. And this is the golden ratio. Anything that follows this ratio is considered a golden whatever it is. So that's just an interesting little piece. And again, historically, it's very appealing to the human eye for whatever reason. The Greeks used it. Nature uses it. I'm willing to bet a lot of advertising agencies also use it, just because it's, for whatever reason, whether it's nature or the human brain or whatever it is, this is very appealing. That's why they call it golden. So hopefully that will at least give you something to think about, but more importantly, go back and look at the idea of polygons being similar. That'll be the important part. And look at that, study your proportions, study your properties, and you should be good to go. Good luck.